Okay, in this section, we're going to talk about continuity. Let's start with a graph of, some function here, which we got by connecting points. This is a graph of continuous function. We don't see any break here. We can draw this graph without lifting our pen. This is another example, which is the graph of function f of x. As you can see that at point 1, there is a jump. At point 2, there is a circle, and then the value of the function at 2 is 2. At point 4, again, there is a circle, and the value of the function at 4 is a half. So this function is not continuous. This graph is not continuous at point 1 because of this jump, at point 2 because of this open circle, and at point 4 because of this open circle. This is the definition of continuous function. Let C be a real number that is either an interior point or an endpoint of an interval, the domain of f. The function f is continuous at C if the limit of the function when x approaches to C is equal to the value of the function. The function f is right continuous at C or continuous from the right if the limit of the function when x approaches to C from the right side is equal to the value of the function. Function f is left continuous at C or continuous from the left if the limit of the function when x approaches to C from the left side is the value of the function. So basically, a function is called continuous if continuous at point C if the limit of the function when x approaches to C from both sides is equal to the value of the function. So in this example, as you can see here, there is nothing to the left of A, there is nothing to the right of B. So at point A, the function is called continuity from the right. A function is called continuous at A from the right because there is nothing on the left side. Similarly, this graph is continuous, you know, to the B from the left. And in between A and B, the function is continuous from everywhere, from two sides, the two-sided continuity. Look at this example here, this graph here. As you can see that there is a jump, and because of this jump, there is a break. So there is open circle, and then the value of the function is start from here to the right. This kind of continuity is called, this kind of discontinuity is called jump discontinuity. So whenever we see this kind of jump, the function is not continuous at that particular point. This is the test we're going to use whenever we try to find out either function is continuous or not. That's called continuity test. A function f of x is continuous at a point x equal to c if and only if it meets the following three conditions. The value of the function at c exists, the limit of the function when x approaches to c exists, and then limit of the function and then value of the function at c should be equal. So this if and only if means if function is continuous at c, this three condition holds, and similarly if these three condition holds, then we can say that function is continuous at that point c. So whenever we try to do the problem, whenever we try to check either function is continuous at c or not, we have to check these three situations. One example here, this is a graph of function 1 over x, and we know that the domain of this function is negative infinity to 0, union 0 to infinity. We know this function is not defined at 0. On this domain, as you can see the graph, this function is continuous everywhere. So the function 1 over x is continuous over its natural domain. This is its natural domain. It is not defined at the origin, so it is not continuous on any interval containing 0. These are some properties of continuous function. If you have two functions f and g, both of them are continuous at some specific point c, then these following algebraic combination are continuous at x equal to c. So if two functions are continuous, their sum should be continuous, their difference should be continuous. Whenever we multiply, those continuous function by some constant, that should be continuous. The product should be continuous. Division or quotient should be continuous, but make sure that the value of the function on the denominator at that particular point should not be equal to 0. The power of continuous function with positive integer power should be continuous, and roots of continuous function should be continuous. So let's see some example here. This is the graph. State whether the function graph is continuous on -2 to 5. So -2 is -3, +5 is, you can see that the graph is smooth. You know, there's no break, there is no jump, open circle. So that means this graph is continuous everywhere. Okay, so this is continuous on -2 to 5. Continue -2, 5. Okay, so this is another example. Determine the points at which the given function is continuous. So this is the function we have given. As you can see, the function, this function is difference of, let's say, h of x, which is 11 over x minus 10, and g of x, which is 2x. So this is a rational function here. Okay? We can see that this function is continuous everywhere except 10, because at 10 the function would be undefined. So h of x is continuous everywhere except 10. Everywhere except 10. Continuous on, from -infinity to +10, union +10 to infinity. This function is continuous everywhere except 10. And this function g of x, it's continuous everywhere. Continuous everywhere. So that means all real numbers. So now when we combine them by using this negative sign, meaning when we find the difference, this function should be continuous everywhere except 10. 10, this restriction coming from h of x should implies for the combination as well. So by looking this, we can say that f of x is continuous everywhere except 10, or continuous on -infinity, +10, union +10 to infinity. Similar, this is another example. This is a combination of two different functions. Absolute value of 5x minus 6. Let's say this is h of x, this is g of x. We try to plot the graph of h of x. We try to see the graph of h of x at x equals 6 over 5. The value would be 0. At 0, the value would be 6. Absolute value function. This is the graph for h of x. And for the g of x, because it's a sine function, so the graph should look like, something look like this. Keep going. As you can see that both of these graphs are continuous everywhere. There is no jumps, there is no break, there is no open circle. So when we take sum of these two graphs, the graph of this function, which is sum of these two graphs, it should be continuous everywhere. So that's why this function is continuous everywhere. So the answer is y is continuous everywhere, meaning -infinity to +infinity. There is no restriction. At what points is this function is continuous? As we know, sine x from previous problem, sine x is continuous everywhere. This 3x, which is a linear function, that is also continuous everywhere. But in this case, we have to be careful. This is 3x, and sine x function is this. Okay, so both of them are continuous, but because this 3x is on the denominator, we are going to ignore that case where this function gives you 0. So meaning this function is continuous everywhere except 0. Y is continuous on negative infinity to 0 union 0 to infinity, meaning we are ignoring 0. Okay? At what points is the following function continuous? So to find out the points, first of all, the only problem it might have is at 2, because you can see that the first part is continuous on on the numerator and on the denominator except 2, because at 2 the denominator would be 0. So this function is continuous you know everywhere except 2. So now check at 2, we need to just use this definition of continuity. This is the definition. At any point a function is continuous if these three conditions satisfy. So we know that this function is continuous everywhere, and we don't know about the 2, so we need to check at 2. So for that we need to find out the limit of the function, when x approaches to 2. So what is the limit of the function when x approaches to 2? So for limit of the function we are going to use this value when x approaches to 2. For finding the limit, we need to find the factor of numerator, which is x minus 1 and x plus 1 and x minus 2, and on the denominator there is x minus 2. So x square minus x minus 2 can be written as x plus 1 times x minus 2. So we can cancel this. And now to find out the limit when x approaches to 2, this should be 2 plus 1, which is 3, which is actually the value of the function at 2, So as you can see that we have the limit of the function when x approaches to 2, which is 3, and which is actually the value of the function at 2. That's why this function satisfy the definition of the limit, this definition at 2. We already knew that this function is continuous everywhere, and we did not know about the 2, so we found limit, and then we compared that limit with the value of the function, and we found that yes, the limit of the function at when x approaches to 2 exists, which is 3, which is the value of the function. So that's why this function is continuous at 2. So the conclusion is f is continuous everywhere, meaning continuous on negative infinity to positive infinity. Let's look at another example here. We have given a piecewise function, and we need to find out what value of a is the following continuous at everywhere. For what value of a? So we need to find out the value of a for which this function is continuous. So we can use the same approach like here. Everywhere else we don't have any problem. Less than 4 or greater than 4, both of these paths are continuous. On the top, this is parabola, so that's a continuous. On the bottom, this is the linear function, so that is continuous. So on the left side of the 4 and on the right side of the 4, we don't have any problem. The only situation we need to check is at 4. And this function would be continuous at 4 if the limit of the function when x approaches to 4 from the left side is equal to the limit of the function when x approaches to 4 from the right side. And so let's find out the limit of the function when x approaches to 4 from left side. So for that we need to use this part. So the limit of the function x approaches to 4 from the left side can be found by using this x square minus 11. So remember, this is just a sign, this is just you know notation for approaching from the left side, but the value of the x you have to plug here is 4. That is 4 square minus 11, which is 16 minus 11, which is 5. So that's the left hand limit. What about the right hand limit? Right hand limit of this function when x approaches to 4 can be found by using the second value 2 times a times x, Whenever we try to find out this limit, we just have to plug x equal to 4, and 2 times a times 4 is 8a. So this function would be continuous at 4 if the value of the function at 4, which is 8a, should be equal to the limit of the function, which means the left hand limit and right hand limit should be equal. Okay, the left hand limit and then right hand limit should be equal. So that is the only case the limit exists. So we can say that the left hand limit is 5 and then right hand limit is 8a. So that situation happens. If that situation happens, then the limit of the function exists, and that would be equal to the value of the function at 4. The value of the function at 4 can be found by here. So if we solve this one, then a would be 5 over 8. So when a is 5 over 8, this part would be 2 times 5 over 8, which is 5x over 4. 5x over 4. Okay, 8a equal 5, a equal 5 over 8. So when x is 4, which is 16 minus 11 is 5. So when a is 5 over 8, I'm just trying to plug the value of the function here. When x is 4, 8a, so that is 5. Yes, that's right. So for a equal 5 over 8, now this function becomes you know x square minus 11 on the left side of the 4, and 2 times a, which is 2 times 5 over 8, so which is 5 over 4 times x when x is greater or equal to 4. So this function is continuous everywhere. Okay, so whenever we try to find the composition of the continuous function, then that composition should be continuous. From this theorem, composition of continuous function: if f is continuous at point C and g is continuous at the value of the function at C, then their composition is continuous at the origin point. To visualize that, let's see that your function f is continuous at C, and the value of the function at C would be f of C. And we know that this function z, the next function, is continuous at this point, then the value of the function at this point would be z at f of C. Now this is coming from composition of two different functions. So now if both of them are continuous, then we can say that their composition should be continuous. That's from this theorem. So whenever we try to find out the limit of the composition function, finding the limit is very easy by using this theorem. If the limit of the function when x approaches to c is b, and z is a continuous function at point b, so remember z should be defined at b, then we can find the limit of the function z at f of x, which is basically b, so which is the value of the function at b. There is one more result theorem which is very useful. That's called the intermediate value theorem for a continuous function. If f is continuous function on closed interval ab, so if the function f is continuous from point a to point b, and if y0 is any value between f of a to f of b, so y0 is anything from here to here, then there should be a point on this interval such that the value of the function is y0. Basically, intermediate value theorem means if there is a starting initial value of a, the minimum value of the function at some point, we don't care either it's a or it's b, and there is a maximum value of the function on this interval, then we should be able to find out any value between that minimum and maximum. Okay, we should be able to find out any value between that minimum and maximum, so there should be no jump. That's what this intermediate value theorem says. So you can see that the value of the function at a is f of a, the value of the function at b is f of b, so we should be able to find out the graph for any value in between this f of a and f of b. One example, as you can see that this is the graph of a function f of x. At 1 the value is 0, at 4 the value is 3. So to be a continuous function using this intermediate value theorem, we should be able to find out any value between 0 to 3. But as you can see that in this graph there is a break from 2 to 3, so there is no value, where we can find out this value 2 to 3. So that's the reason, because of this intermediate value theorem, this is not continuous. Intermediate value theorem means there should not be jump or break like this. We should have, a point where this we should have the value from 2 to 3. Okay? So that's the section continuity.